I'm going to be telling you a little bit about our research on using AI to help address big sustainability challenges. So as probably many of you know, our society is facing some pretty formidable challenges to sustainable development. There is close to 1 billion people around the world living in extreme poverty, hundreds of millions of people that don't have enough to eat every day. Climate change is real, despite what you might have heard recently. It's really threatening the survival of many societies around the planet. We're going to need to find new, clean, and affordable sources of energy, find ways to preserve biodiversity, and generally close the gap between developing and developed countries under many metrics. These were just some of the development goals that were identified by the United Nations as part of the 2030 Development Agenda that really identified the big societal challenges that the international community should focus on in the next decade or so. And clearly, these are very important problems. They are also very hard, and one of the reasons is that these issues are extremely complex. They involve these global scale phenomena that are very difficult to model, to predict, and to control. Now, on the positive side, I think we are in it's really an exciting time to think about these problems because new technological developments, I think, are really creating huge opportunities for coming up with new innovative solutions to attack these problems. In particular, we are in the middle of a sensing revolution that is creating a whole new set of data sets that are available globally with a very high resolution that contain a lot of information about these sustainability problems. I'm thinking about our global sensing capabilities that are really booming in terms of the kind of data that we can get from phones and smartphones and through crowdsourcing or remote sensing through satellites and so forth. All these new technological developments, they're creating a wealth of data that contains a lot of information about the health of our changing planet. The challenge is that all of this data is massive and it's unstructured. And so far, this has really largely prevented its use in informing both research and policy. And so the goal of my research is to really change this and develop AI techniques that will enable us to extract actionable insights from all of this data, and more generally come up with computational approaches that will help us find better solutions to these problems. So to give you a sense of the kind of research problems, let's look at poverty eradication, which is the #1 goal on the UN list. Unfortunately, the kind of data that we have about poverty is extremely scarce, especially in developing countries. You can see here a map of the African continent showing for each country the availability of nationally representative surveys in the decade from 2000 to 2010. And as you can see, many countries are white, meaning that there is no data available for that decade for that country. And as you can guess, with this kind of data, we can set as many goals as we want, but if we don't have data to measure progress toward these targets and figure out, inform research, figure out whether policies are working or not, it's going to be very, very, very challenging to meet our goals. Now, on the other hand, high-resolution satellite images are available in pretty much every corner of the world. And as you can see in these few examples, they contain a lot of information about these kind of socioeconomic outcomes that we care about. You can see houses, you can see roads, you can see information about the infrastructure, you can infer something about economic activities, mines, agricultural productivity, transportation infrastructure, and so forth. The challenge is that this data is unstructured. These are just images. And so the question is, how do we actually make sense of these trillions of raw pixel values at scale, in a really scalable way? And here is where machine learning and AI comes in. In the past few years, we've made a lot of progress in many key visual perceptual tasks, like recognizing objects, classifying images, and so forth, mainly due to the rise of these new deep learning techniques, so very high capacity models that we can train to solve fairly complex tasks. One of the challenges in this space is that images are very high-dimensional objects, and there is a lot of variety in real-world images. So to train these systems to perform well, we typically need a lot of labeled examples, a lot of training examples of how to solve these problems we care about. So ideally, we would like to build a system that for our application, that solve this kind of problem. It takes as input high-resolution satellite images, which are widely available around the world, and uses them to predict the kind of poverty estimates that our colleagues desperately need. The challenge is that we don't have enough training data to build these systems. And so, you cannot just train end-to-end the latest convolutional neural network to solve the problem. So what we had to do was we had to come up with some new techniques to actually make, which involve a combination of neural networks, transfer learning, semi-supervised learning, to actually maximize the amount of information that we can extract from the limited labeled data that we have. And this was presented in a recent science paper that you can find more details about that in the actual paper. So I'm not going to tell you much about how the models work, but just to give you a sense of some of the ideas that we included into the models. One key feature of our problem is that we're trying to predict, to create poverty maps, where we're trying to predict poverty as a function of space and time. So rather than making predictions individually at each location, sort of independently, what we can do is we can leverage ideas from statistics and geostatistics and use these powerful Gaussian processes models that essentially corresponds to collections of random variables over space and time that are correlated in some way. And we can combine these ideas with state-of-the-art neural networks, building a model that looks like this. So we have, for each location, we feed high-resolution images through our neural network, which produces an estimate. And then we combine all of these estimates using a Gaussian process to capture this prior knowledge that we have about the domain, about the kind of spatial-temporal correlations that we would like to capture. I haven't told you much about the details, but again, you can find it in the papers. Another key property of this probabilistic approach is that this Gaussian process model will not only provide predictions about the poverty estimates that we want to come up with at different allocations for which we don't have actual labeled data, but it also allows us to quantify uncertainty. So given a location for which we want to make a prediction, the model will not only give us a number, represented by the black line in this cartoon, but it will also tell us how uncertain the model is about the prediction. It will tell us what's the uncertainty at that point. And this is important because we can then use this for semi-supervised learning. The problem in this setting is that we have very limited labeled training data, but we have a lot of unlabeled data. We have a lot of images available, and we would like to somehow use them to improve our model. So what we can do is we can come up with a new learning objective that combines the typical kind of loss function and is trying to fit the labeled data as well as possible with this new objective that is sort of trying to say, well, for unlabeled locations, we don't know the actual ground truth values, but what we can do is we can look at the predictions made by our model and we can try to find the parameters that minimize the uncertainty at those locations. And in this way, we can actually use all the unlabeled data that we have, and we can improve the accuracy of our model. Here you can see some examples of the kind of filters, the kind of features that the model learns to recognize in the images. You can see an image and the corresponding pixels that the network thinks are important for predicting the things we care about in that image. You can see that the model learned how to identify roads, waterways, houses, buildings. There is even a filter looking for swimming pools. The model figured out that that's predictive of these kind of socioeconomic outcomes we care about. And what's exciting here is that we never told the system look for roads or even told the system this is a road, this is a house. The system figured out by itself that those are the important features to identify in the images. We can then use all these features to actually use them in a second statistical model to make predictions about the poverty outcomes that we would like to model, like asset-based or consumption-based measures of wealth. We tested it in 5 African countries, and we got very good results. We can explain up to over 60% of the variation in the data, which is better than any other technique available so far, including ones that use phone data, which has all kind of privacy issues. Of course, the model is not perfect. There is some things that you cannot see from the images, but it's doing quite well. And what's exciting is that the only input that we need are images, which are available everywhere. They are cheap to obtain. They're passively collected by satellites. And we can use them to construct these poverty maps with really unprecedented resolution. Here you can see a couple of examples in Uganda and Tanzania, but we did it for several other countries. And what's really exciting is that all we need as input are images. And so as we get new images, we can keep the models up to date in a very inexpensive and still pretty accurate way. We've provided these estimates to a number of partners, Department of State, World Food Program, and World Bank. This is a map I sent a couple of months ago to the World Bank about Somalia. That's a country where they cannot, there is no data. They cannot send people to collect data because they would get kidnapped or worse. And so, they're pretty excited about these new estimates that we can provide because we can do it essentially for free in every part of the world. We got quite a bit of interest in this work from media. Bill Gates was tweeting about this. It was featured in several reports in the White House. It was also identified as one of the world-changing ideas of 2016. You might have seen it on Scientific American. And so we're really, really excited about seeing what kind of new approaches we can find to tackle these very important problems in collaboration with our partners. Another thing that I'm very interested in is using these techniques to deal with other sustainability problems, in particular food security. There are hundreds of millions of people around the world that don't have enough to eat, and the problem is going to be worse and worse. There is an estimated 2 billion more people that we're going to have to find a way to feed by 2050, and it's pretty clear that information technology and AI will have to play a role in this. We looked at whether we can use similar ideas, so use cheap, inexpensive, passively collected data sources like remote sensing data, crowdsourced data, social media data to predict food security outcomes and track agricultural productivity. So we used a very similar pipeline where we use images as input, our deep Gaussian process model to come up with predictions. Here you can see one example where we develop a machine learning model that takes as input a sequence of multispectral images collected by satellites in the United States and basically tracks the health and the growth of plants over time and uses this model to make predictions about, in this case, soybean production in the United States at the county level. And you can see how the model is updating the predictions as it collects more data from the satellites. It turns out this is, of course, very inexpensive to do, and it's also very surprisingly accurate. It actually does better than even the estimates produced by USDA, which require surveys, requires going into the fields, calling up farmers, and things like that. So it's much more scalable, it's fairly accurate, and we recently won the first prize at the World Bank Big Data Innovation Challenge because this project, we are competing with hundreds of other submissions from over 40 countries in the world, but this really has a lot of potential for coming up with new scalable approaches to deal with these food security challenges. In particular, we are very excited about applying the techniques. So we've demonstrated an application in the US. We're pretty excited about using this in Africa, in Kenya. We're partnering up with the Acre Fund, which is a nonprofit that is trying to improve agricultural productivity in developing countries through training, insurance policies, and other programs. And so we're really excited about the possibility of scaling up to the entire world, and especially developing countries. We've also been looking at predicting food prices, measures of hunger, and combining sort of these models of agricultural productivity with our poverty models. We want to improve our models to make predictions at the field level. We've been doing it at the county level, but soon we will be able to improve our models even more thanks to new and even more accurate and sources of data. And of course, we want to use these techniques to actually help us make better decisions. Fundamentally, that's what we want to do. And so we want to couple these predictive models with the decision-making techniques, also from AI and optimization, to help us make better decisions based on these predictive models that we built. So yeah, I hope I convinced you that there is lots of room for using AI and machine learning techniques to deal with these very important challenges. There is a lot of concern about the potential threats that AI poses to society, and indeed that's one issue. But I like to be optimistic here and think about the massive potential that I think there is here for using this technique for really benefiting society at large and dealing with these very important problems and coming up with accelerating human progress, coming up with new innovative solutions to these very important problems. There's a lot more work to be done, and we've done also other things, but of course the time was limited, so if you want to learn more about the kind of projects we work on, please talk to me. Thanks.
Stefano is a certified rock star, as you've seen, and his incredible success in getting awards for everything he's doing comes from combining advanced machine learning with knowledge from subject matter experts. And as you can see, he's done that in a series of areas, including many that he didn't have a chance to talk about this morning. We have a few minutes. Any questions for Stefano? Yes?
Hello? Oh, okay. So thanks for the very interesting presentation. Working for a global reinsurer, I can only confirm that there is certainly huge potential. I actually have two fleshy questions. One is, how do you generally validate the accuracy of any map that you can generate? And the second one is, how can you really sort of manage or draft down a roadmap to how many different kind of maps can you extend? So you talk about poverty, I could talk about crime rates, pollution, traffic accidents, whatever.
Yeah, great questions. So in terms of evaluating the models, we use standard kind of techniques like cross-validation to sort of try to see to evaluate the predictive power of the models out of sample. For example, in the case of poverty, what we can do is we can build a model based on data collected in one country, and we can test it in a different country and see how well it does compared to ground truth data. So pretend I don't know it, come up with an estimate and compare how well it does. And so all my evaluations that I showed before were done in this way. So they're really out of sample, so they should be fairly realistic in terms of what you would expect from the model when you apply it to previously unseen data. In terms of possibilities, I agree, it's sort of really endless. I think there are so many things we can do with this data. We're really just scratching the surface and trying to, basically look at that list of what are the most important problems, according to the United Nations, and try to go about them in order. Like poverty is number one, food security is number two. So we've been looking at those problems because I think that's where we can have the biggest impact. But indeed, there is a lot more we can do, and I hope to see more work coming out on using these techniques for dealing with these very important problems. I know there are many people, and even at different universities, that are starting to think about these problems, and hopefully we can build a community both from researchers in academia, people from industry, NGOs, and all get together and find better ways to deal with these problems.
Do we have another question? Perhaps right here? Oh, sorry. Perhaps right here. I guess we're going there first, and there. If they're short, we can try to get two more in.
Yeah. First of all, nicely done. Huge fan of satellite imagery and for good applications. Have you thought about applying these methods to other sources of imagery or even other modalities of satellite imagery?
Yeah, good question. So we looked a little bit into crowdsourced images on the ground, and we couldn't find enough sort of data to actually build something useful on it. In terms of other modalities, do you mean like multispectral images? Yeah, so in the context of, say, the agricultural work, the food security work that we did, we were looking at multispectral images, not just RGB. Actually, the visible bands don't actually do much. It's really like infrared and near infrared that sort of gives you the most. And it's actually quite interesting because it turns out that the kind of bands that domain experts, remote sensing experts, thought would be the most informative about this kind of outcomes turn out to be not as important when we use these more modern machine learning approaches where we try to discover automatically, let the data speak, and try to figure out what is really important for making these predictions. Turns out that our model used bands that were previously not thought to be as important. And so that's also another exciting kind of insights that you can derive because, you're trying out these more data-driven approaches can actually give you new insights also in terms of the actual remote sensing domains.
I had a quick question. So how does the model perform in cases where there are attempts to sort of model or sort of hide the state of poverty, like for example in North Korea, or governments acting to do things to create, facades? And also, how do you see it working to, become a gold standard for the UN or other organizations in defining poverty itself?
Yeah, so we haven't tried, we only evaluated in Africa, and so we in the paper, in the science paper, we evaluated in 5 countries. Now we are scaling up to the entire African continent, so which involved a lot of sort of systems building, but we're almost there to sort of rolling it out and let people use the maps and keeping them up to date. So develop like a fairly scalable cloud-based platform to do that. In terms of becoming the gold standard, I don't think it will ever be the gold standard, in the sense that, of course, it has limitations. Like, there's only so much you can see from images. There are just things you cannot see inside people's houses. I think the way I see it is helping is that it's first of all, it's inexpensive. You can keep it up to date much more frequently, and you can combine it with actually data collected on the ground. I don't think we will ever get rid of surveys, but I think it can nicely complement them, both in terms of just collecting data and then combining it with these new unconventional data sources, but also helping us coming up with better strategy for collecting data. So we're talking with the World Bank about figuring out how to optimize the data collection process based on these estimates. Can you sort of figure out where you should send the survey takers to actually maximize the information that you get out of the surveys? So I think there are lots of opportunities, but we haven't figured out yet what's the best way to use it.
Please join me in thanking Stefano.